Hi guys, so in the last video we have seen how the sentence "I love NLP" gets into the embedding, and the positional encoding was taken and added to the output of the embedding, and we got this result. Today we'll see how this result gets into the self-attention, how the output of this self-attention is added with the input. So I can divide this to half. So the last output, if you can remember, the last output was something like this. .1, 0.5, 1.44, 1.44, 1.7, 0.19. This was the last output of the embedding with the positional encoding, and we said that the dimension is IS by E, where IS is the input size, number of words in the input sentence is 3. We have 3 words, and E, embedding dimension, is 2. So the formula for self-attention is this. Let me write it. Q K transpose divided by square root of E times V. Okay, so in self-attention we have keys, queries, and values. So initially this is your key, this is your query, and this is your value. This is the key, it is the query, and it is the value. Okay, so what happens behind the scenes is, but before that we need to compute the new keys, queries, and values that we can plug into the formula, into this formula, to get the output of the self-attention. So the way it works is, behind the scenes, PyTorch creates this weight vector of dimension 3 times E by E, and it is 6 by 2. So 3 times E is 2 by E. And PyTorch also creates a bias of dimension 3 times E by 1. And in this case it is 6 by 1. Okay, so I'm going to take the transpose for convenience, and we will see why we take the transpose. And when we take the transpose, it's going to become 2 by 6, and this becomes 1 by 6. Okay, so let's try to visualize what this W is. W is, 2 by 6. Oops. Okay. 1, 2, 3, 4, 5, 6. So, okay, this is 1 dot. This is also 1. Okay, so this is 2 by 6. So usually the way it's done is, this part of the weight vector is the weight of this key, and this part is the weight of the query, and this part is the weight of the value, and each of them have a dimension of E by 2. This is also E by 2, E by 2. And a bias is also created randomly at the beginning, and this bias is something like this. It has a dimension of 1 by 6, and this part of the bias is the bias of the key to compute the new key. This is the bias to compute the new query. This is the bias to compute the new value. and all have a dimension of 1 by e, 1 by e, 1 by e. So usually to compute the new key, you will take this input multiplied by this weight and add it with this bias. For the new query, take the input multiplied by this weight and add it with this bias. For value, take the input multiplied by this weight and add this with this bias. But since key queries and values are all the same, we can use a shortcut. So what we can do is we can take the input, this input multiplied by W plus B. The input is something like this. It's a tensor multiplied by W. It's also a tensor this plus the bias. And input has a dimension of 3 by 2. W has a dimension of 2 by 6. So that's why we took the transpose to make the multiplication possible, and add it with the bias, which is 1 by 6. And the result of this is 3 by 6, 1 by 6, and we get a result that has a dimension of 3 by 6. Sorry, is it 3 by 6? Yes, it is 3 by 6. And this 3 by 6 is actually the same as IS by 6. Okay. So let's see what this output, this tensor looks like. So it is something like this. So this tensor, actually this part of the tensor is the new key, this part of the tensor is the new query, and this part of the tensor is the new value. Key, query, and value, and each of them, they all have a dimension of, all this key, query, value have a dimension of 3 by 2. Okay, so in the formula we need to divide the query by the square root of e. In the formula it's written like query times k transpose divided by e, but we can just say query divided by the e transpose first. So the query, this new query, this one, is going to be query divided by square root of e, and the dimension will not change. It is still 3 by 2. New dimension is still 3 by 2. And next we need to multiply the query, this new query, and k transpose, this transpose of k, and query is a tensor of something like this. Let me write it, 3 by 2, and it's going to be multiplied by the transpose of k, which has a dimension of 3 by 2. When we take the transpose, it's going to become 2 by 3. So this is k transpose, and the result is a tensor that has a dimension of 3 by 3. Okay, so let me write this in something bigger, because I want to explain something. Okay, so this is the multiplication of this. We need to then push it into a softmax, and in softmax, what you need to do is take this and divide it, and take the exponents, then divide the exponent by the summation of all the exponents of this row. For example, take this, take its exponent, then divided by the exponent of the summation of exponents of all the values in the row, and that is the softmax. The formula for softmax is, let me write it here. Zi divided by summation of j1 then k e to the zi. Okay. And when we take the softmax, we will end up with something like this. A very, very interesting tensor. The dimension will not change when we take the softmax. It is still 3 by 3. But what's interesting is that, okay, let me actually write something 0. Maybe 2, 0. This is 37, 0.1, 0.5, 0.4. This is 0.3, 0.1, and this is 0.6. So the summation of all the rows is sums up to 1. And what this means is the dimension is 3 by 3, which is the same as is by is, and we call this result of the softmax attention weight, or AW, and this represents I love NLP. I love NLP. What this value represents is the amount of attention I should pay to itself, and this represents the amount of attention love should pay to I. The amount of attention NLP should pay to love is 0.4. This is what this means, attention weight. Finally, we need to take the attention weight AW and multiply it by V. V is this, 3 by 3. Attention weight has a dimension of 3 by 3, multiplied by V, which has a dimension of 3 by 2. And the resulting tensor has a dimension of 3 by 2. And PyTorch also, so this is after this self-attention. We have completed the self-attention, but it's not yet over. PyTorch also creates weights, output weights, and output bias, and this output bias has a dimension of E by E. Bias contains dimension of E by 1. So the final output is going to be this attention weight, this one, multiplied by OW, then added to OB. This has a dimension of 3 by 2. This one has a dimension of 2 by 2. But we are going to take the transpose because we took transpose here. This is going to be 2 by 1 transpose. Okay, and the result is going to be 3. We'll have a tensor of dimension 3 by 2. So this is output of the self-attention, but we need to find the output of the self-attention, which is this. we need to add it with the input. The input has a dimension of 3 by 2. The output of the self-attention has a dimension of 3 by 2. And we will end up with one tensor that has a dimension of 3 by 2. And that tensor I've actually written it is 1.6, 0.3, 1.9, 1.3, 2.3 and 0.0. And it is this when we add it. It is after the addition, this is what goes into the final layers. This one. This. Thank you and see you in the next videos.